I just recorded about 5 minutes muted. I have to start all over again. Okay, I'm going to try to do this quick. Just catching you up to speed, right? We're getting ready to jump into propositional logic, where we'll learn how to evaluate a deductive argument to check, to make sure, is it valid or invalid? And we can use very precise methods, just like in math, right? And so to get ready for that, we have to learn about these four basic elements that we use in propositional logic. These four logical operators, right? Which is conjunctions and statements, right? A and B, it's sunny and warm, like this one right here. Disjunctions, which are or statements, so A or B. And then conditionals, which are if A, then B, right? We've looked at conditionals a lot. Remember, the first part of the conditional is called an antecedent, and the second part is called the consequent. And then we'll look at negations, which just say not P, right? You can see that the not is a little bit different from the other three. The other three always involve two statements, and it's sandwiched in between the two statements, like you can see right here. It's sunny and warm, right? Two statements kind of held together by the logical operator. Not functions slightly differently, right? But we'll get to that. And so once you learn each of these four operators, then we can go ahead and look at arguments and see whether they're valid or not. One of the ways to learn about the operators, to know how they function, is to set up a truth table, because that sort of shows what their function is. So we did that for the conjunction right here, right? It's sunny and warm. Intuitively, you just know, right? When would that statement be true? If someone actually said it's sunny and warm, in what situation would that be true? Well, you know intuitively, because you know what the word and means, that would only be true if it is sunny and it is warm, right? And that's possible world one, right? And there's just four possibilities when you have two statements. So whenever we set up a truth table and there's just two statements, it's always going to look like this, right? So in world one, where it is sunny and it is warm, then it's sunny and warm is true. So that's why it says T and then another T right at the end for it's sunny and warm. The truth of the small statements, along with how the operator works, determines the truth value of the compound complex statement. And then we can see in the other worlds that it's going to be false, because in all the other worlds, either it's not sunny or it's not warm, or it's neither sunny nor warm, right? So that's why we have FFF underneath. It's sunny and warm, right? This should make sense, right? If you know how to speak English and, it's sunny and warm, well, if it's not sunny or if it's not warm, if it's neither, then what I said was false, right? So we can take that statement, it's sunny and warm, we could take it for a spin across logical space. You know, when you take a car for a spin, right? That's what I'm trying to evoke here. The idea of going for a little trip, right? That's what I'm trying to say. We can take that single statement, it's sunny and warm, and take it to possible world one, right? Is it true in that world? Yes, it is true in that world. Let's take it to possible world two. Is it true there? No, it's not true there, right? Etc. And then we can do that for the other operators as well. We can do that for it's sunny or warm, right? Take it across logical space. And we could do it for if then. If it's sunny, then it's warm. We can do the same thing, right? We can do the same thing for negations, but again, they work slightly differently. It'd have to be something like it's not sunny, right? And then we take that across logical space. We'll get to that later. And notice that whenever we have two statements and we're doing a truth table for it, we have the two statements here, it's sunny, it's warm. Doesn't matter what the statements are, we're always going to set it up in the same way, right? So that we always are making sure that we have each of the possible worlds captured in our truth table. So underneath the first statement, it's always going to go TTFF. Underneath the second statement, it's always going to go TFTF, right? And that way you get a nice spread of each of the possibilities, right? The first world where they're always both true, and then the fourth world where they're always both false, and then the world two and world three where they sort of take turns being true and false. Right? And so it's always going to look like that for the two statements. So, whenever we have two variables, right, A and B, P and Q, X and Y, whatever it is, right, those stand for simple statements. Whenever we have two simple statements or two variables, it's always going to look like that right there. And then on the side next to it, we can sort of lay out a statement like a conjunction or a disjunction, whatever. Or we can take a whole argument and see what happens with the arguments. That's what we're going to do soon, right? Like, we're getting ready for it. Before we can really do that, we need to understand fully how each of the logical operators work. So let's do that today. And this should not take all that long. I feel like I'm kind of behind from where I want to be. It's always hard when the online classes are just difficult. It's difficult to gauge where everybody's at, right? And it's always difficult too when you only have 8 weeks and I have to just focus on certain things and leave out other things. If this is a full semester, there'd be a lot more time to cover everything. So here I have to make all these decisions about what is essential, what is not, right? And I feel like it's all essential, so I can't leave anything out, but that's just not possible. So I have to make choices. Okay, so like I said, for the game of logic, right? I like to call it a game because it has a point and there's some rules and there's some pieces, just like a game of chess or something like that, right? Where you learn how each of the pieces work and then you learn how to play the game. First, you have to know what the pieces do, right? Before you can jump into the game. So before we actually play the game of propositional logic, let's get a little bit of a clearer understanding of how each of those four operators work. Even though I think being an English speaker, you will already know what these terms mean on some intuitive level. But here we're going to make it all crystal clear and very logical, right? Appropriately so. So each of the four operators, hopefully if I just ask you right now, what are the four operators? Hopefully you know, hopefully you can tell me, right? They are the conjunction operator, the disjunction operator, the conditional operator, and the negation operator, right? So in order to fully define this, we're going to do that using a truth table. Notice you could also define it just in English. I could just say, well, a conjunction, an and statement, that's the type of statement that can only be true if both of the things are true. For a disjunction, I could just say, well, a disjunction, an or statement, is going to be true as long as one of the two statements is true. And it'll also be true if they're both true, because remember, we're using the inclusive sense of or, where what we mean is at least one of the things has to be true, but they could both be true. Like if I ask, do you want cream or sugar, right? You don't have to choose just one or the other. You could choose both. So that's the kind of disjunction that we're dealing with here in logic. We're defining it in this way, right? So I could just say, well, a disjunction, how does that work? Well, it's true as long as at least one of the disjuncts is true. A conditional, how does a conditional work? Well, conditional is really, that's only going to be false in one scenario. It's only going to be false if the antecedent is true and the conditional is false, right? If I promise you that if you give me $10,000, I think it was 100 originally, but I'll settle for 10. Right? If you give me 10K, I will eat a worm. Well, then if you get together, and I encourage you to do this, get everyone together and pool up that money and offer it to me, say, here's your 10K, right? And then I chicken out of eating the worm. Well, then I had said something false, right? So conditional, the rule is it's only false in one scenario, where the antecedent, the first part, if A, then B, right? A is true, and the consequent B is false. And all the other scenarios, it'll be true. And then negations, how they work is they just flip the truth value, right? So if you said something true, and then I say not that, then I said something false, right? If you said something false and I negate that, then I said something true. The negation is the simplest one, but I swear that's the one where if you explain it, it gets confusing. Just kind of hold off on the negation. Don't worry about that one yet. We'll get to that one. But anyway, I explained the rules for each of these just in ordinary English, but that doesn't make it as precise as really laying it out with the truth tables. So that will really be able to show you, right? And so this time, instead of saying it's sunny, it's warm, right? Instead of using English, we're going to use logic speak, right? We're going to use the language of logic where we don't use whole statements. We're just going to have a variable like A or B or P or Q that stands for a simple statement. and then we'll use the symbols that we learned about for each of those 4 operators. So conjunction is really the easiest. That's always a nice one to start with. Right? So conjunctions, just to remind you, right, they're and statements. So Socrates is human and Socrates is mortal. That's an and statement, right? We have 2 simple statements. Socrates is human, Socrates is mortal, held together by and, right? Or if I say it's both sunny and warm, that kind of sounds like one simple statement, but really that's also a conjunction of 2 different statements, right? It's sunny, it's warm, and it's being held together by and, right? So that's what conjunctions are. So let's just use the variables P and Q. That's pretty standard for logicians to use P's and Q's. And I sometimes wonder if that's where the expression came from, right? Mind your P's and Q's. Probably doesn't, but it is interesting that logicians use those variables a lot. It's their favorites. But remember, variables, it's arbitrary. You could use A and B, you could use X and Y, it doesn't matter, right? Let's do P and Q. So the 2 statements that we're joining with and, those are called the conjuncts, remember? So P is one conjunct and Q is another conjunct, and then we'll bind them together with that variable and. And for and, we just use the and symbol, right? Really nice. We don't get a fancy logical thing even, right? Just the symbol and that most people already know about. So then to get started, right, what we're doing here is creating a truth table to show how each of these operators works, right? It defines them, right? Just like if I say in chess, the little horsey guy can jump 2 in one direction and then 1 in the other direction, right? That's the rule, right? We're defining what the pieces do. So that's what we're doing here. So to define what each of these operators does, because for conjunction and disjunctions and conditionals, we're always going to be using two statements, 2 variables. It'll always look the same for each of those 3. Right? And it's going to be those 4 worlds that we just talked about, right? Those should be familiar now, right? Where world 1, they're both true. World 4, they're both false. 3 and 4, they're both taking turns being true and false. Right? So if I were to tell you, set up a truth table for the conjunction operator, this would be your first step. You take 2 statements, separate, no operator in between them yet, just the 2 statements that are going to be involved, and then we'll set up the logical possibilities for them, right? Possible world 1, where they're both true. Possible world 2, the possible world jumped ahead a little bit there, where P is true and Q is false. Possible world 3, where P is false and Q is true. And possible world 4, the false world, right, where they're both false. And just to remind you, this just represents all the possibilities that there are for any 2 random statements that you can make. Right? Any 2 statements that are either true or false. Right? If you don't know what their real truth value is, you can at least sketch logical space. It's one of the things that you can know, to use a philosophical term, a priori. Right? That means without experience, without checking, right? You don't need to see what the world is like in order to know that these are the possibilities for any 2 statements. They could either both be true, they could both be false, or one is true and the other one is false, or the other one is false and that one is true. Right? Those are all the 4 possibilities. So whether we're doing a conjunction or a disjunction or a conditional or an argument with 2 statements or 2 variables, this part will always look the same. Right? And to ensure that it always looks like this, remember the trick. Underneath the first variable or the first statement, you go TTFF, and underneath the second one, you go TFTF. And that creates these familiar worlds where the first one is true and the last one is false, and the other ones, they take turns, right? I hope everyone can see that pattern clearly. Then we're going to take our conjunction, right? We're going to put the conjunction operator right in the middle, and we have the P and the Q. So now on the right side of P, Q, right, where we're just listing them separately, but they're just all the different combinations that they can be true or false together, right? How they can be true or false together. Now we have one big statement, P and Q, right? And we'll take that for a spin, right? We'll take that to each of the worlds and ask ourselves, is that statement true or false in that world, right? So if I were to say P and Q, and we go to possible world one, where P is true and Q is true, well, in that world, my statement P and Q would be true, right? We just saw this. We just saw this with the it's sunny and warm, right? It's the exact same thing. If I say it's sunny and warm, that's going to be true only in world one where it's sunny and it's warm, right? So hopefully you can already see how the rest is going to go. And notice here's a little thing that's going to be helpful when we start doing logic. I put the true underneath the sign, right? And that means I'm talking about the truth value of the whole big statement, right? On the other side, we have P and then TTFF, Q, TFTF, right? That just tells us the truth values of each of the statements by their own. But here I have the truth value T underneath the operator. And that means I am talking about the truth value of that whole statement, P and Q, right? So that's where you put the truth value. So we do the same thing here. Right? But if I say P and Q, but Q is false, like in world two, then my statement is false, because an and statement is only true if both things are true, right? Same problem for world three, right? There, P is false, so then the whole thing's going to be false. And then possible world four, where they're both false, right? It's not sunny or warm, then certainly if I say it's sunny and warm, it's also false. So you might say that an and statement is very difficult to please, right? An and statement is usually going to be false. There's only one possible world where a statement like that is true, right? That's world one. Okay, so this just tells you what a conjunction operator does, how it functions. Right? The way in which the truth values of the simple statements affects the truth value of the complex compound statement. So that's chess piece number one, right? We only have a few more to go, so stay with me here. So if I ever say define a conjunction using a truth table, this is just what you do, right? You'd have the P and the Q, lay out the truth values, all the possibilities, and then take the conjunction statement for a spin and ask yourself, right? In world one, is it true or false? In world two, is it true or false, etc. Right? Then you will have defined what it looks like. And it'll look like this every time, right? This is one of these things where, in a game, things change. It doesn't always look the same. But we're not playing the game yet. We're just defining each of the pieces. And this is what the rule is. Just like, chess, right? The little horsey guy can move 2 in any direction and then 1 in the other direction, right? Okay. But then once you actually play the game, right, then the rule doesn't tell us where the horse goes, right? It just depends on the game. So let's do the other ones in the same way, right? We'll do the disjunction operator next. And so since disjunctions are also just an operator that holds together 2 simple statements, right, we can just use the same technique. We can keep P and Q and lay out all the possibilities in exactly the same way. That doesn't change, right? Still just 2 statements that can be true or false in 4 different combinations. So we'll keep those familiar worlds, but we'll just change the and operator to the or operator, right? So now it says, instead of P and Q, now it says P or Q. Right? And so here the rules will be different. Remember that we're doing an inclusive or, right? So that means at least one has to be true. They could both be true, right? It's only going to be false if they're both false, right? And you should know by now, right, that the false world is world 4. So you should already kind of be able to tell that the way this is going to go is probably going to be, well, not probably, it is going to be TTTF, right? Because it's very easy for an or statement to be true. As long as one of the disjuncts is true, then the whole thing gets to be true. So the and statements are difficult to please, right? There's only one scenario where those are true. Or statements those are very easy. They can be true in all sorts of different possibilities. Possible world number one, right? Where they're both true. Sure, P or Q will be true in that world because we're using the inclusive sense, where at least one of them has to be true, but they could also both be true, right? So it's true in world one. Now, if this was an exclusive, right, if we wanted to define it exclusively, all we would do is change the value for that first world. We make it an F, right? But we're not doing it that way, right? We're doing it inclusively. World 2, is P or Q true? Yeah, P is true in world 2, so the or statement is true. What about world 3? Well, Q is true in that world, so our statement that says either P or Q or both have to be true, it's going to be true. Like predicted, it's going to be false in world 4, right? If I tell you this or this, maybe both, but neither of them is true, then I've said something false, right? So again, and statements are very difficult to be true because they're only true in one possible world. Or statements are a lot easier to get because there's 3 different possible worlds where it gets to be true. It's as easy as that. That's all this really is, right? Defining the truth tables. But you'll have to have that knowledge in your mind once we do propositional logic. You'll have to kind of understand how each of these works. And just kind of like check, right? Look at what changes and what doesn't change. On the one side where it just says P and Q, we have all the possible worlds mapped out. That doesn't change. Those are just the possibilities for P and Q. They can both be true, they can both be false, they can take turns, right? Okay. But on the other side, underneath that operator, right? See what changes? When I change it to an and, then everything underneath of it changes. I can go back. When it's an or, it goes T, 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 F. When it's an and, it goes T, F, F, F. And that reflects this idea that I said that an and statement is more difficult to please, right? If we want it to be true. An and statement is only true in one of these worlds, right? That first world. Whereas the or is true in 3 of them. But this difference reflects the difference in how the disjunction and the conjunction work, how they affect the truth value of the compound statement. Okay, now up next is the conditional. And for that we just use an arrow, right? And the arrow means that this says if P, then Q, right? The arrow just sort of, it points from P to Q. It means that if P is true, then Q better be true, right? And that's the rule. All it really is saying is if P is Q, then Q must be true, right? That's the rule. So think of this as stating a rule. And the rule, as long as the rule isn't broken, right, then the rule is in effect, right? So, for example, if the rule is if you're under 21, you can't drink beer, right? Then if I, as someone who's older than 21, am drinking beer, I have not broken the rule, right? That's fine. Or if someone who's under 21 is drinking a Coke, not beer, they haven't broken the rule. The rule is in effect. Right? The only time that the rule is broken is when you have an underage person drinking beer. Right? And so it just goes to show you that rules generally are true unless they're broken. So we don't have to actually see the pattern, right? That's that whole thing about confirmation bias and pattern spotting. If P, then Q, it's just going to be true by default. The only way that it can be false is if there's P being true and Q being false. Right? That breaks the rule. The rule says whenever P is true, Q has to be true. Then if we see P and it's true, and then we see Q and it's not true, then the rule has been violated. In any other scenario, the rule is not being broken, so the rule is being upheld, and we can say that it is true. It's a true rule. So that's why, and obviously in World 1, right, this is why I use the example, if you give me 100K, then I will eat a worm, right? Right now, for example, you're not giving me 100K, and I'm not eating a worm. Both of the things are false, but the statement itself is still true. Because it's a conditional, it's a hypothetical. All it's saying is, all we're committing to is, in this particular scenario where you give me 100K, then I am going to be eating a worm. And if I'm not eating a worm in that scenario, then my statement is false. So, in the technical jargon, right, conditionals, typo, conditionals are only false when the antecedent is true and the consequent is false. Oh, 2 typos right there. Boy. There's an extra C, right? That C doesn't make any sense. That's just the C of consequent, right? So conditional, this is the general rule. Conditionals are only false when the antecedent is true and the consequent is false. Because a conditional just says, hey, when the antecedent is true, the consequent is true. Well, if we see something opposite from that, then it's false. Otherwise, it's just true. So obviously in World 1, right, let's take our conditional for a ride through logical space. If I say if P then Q, and we're in World 1 where P is true and Q is true, great. Yeah, that just kind of confirms the pattern, right? That doesn't tell us much. It just means, okay, nobody's breaking the rule, right? So true, right? World 2 is where we get into trouble, right? In World 2, P is true, but Q is false. Right? That's the world where you give me 100K and I don't eat the worm. Then I lie, right? Then my promise has been broken. Right? Then the rule has been violated, right? Because the rule says whenever P is true, Q is true. But in World 2, P is true and Q is not true. So that means the statement is not true in that world. In World 3, again, there's no rule being broken, right? The rule just says, hey, if there's a P, there better be a Q. If P is true, Q has to be true. World 3 does not violate that rule, right? It's a scenario where, this is possible, right? Even if it's true that I will eat a worm for $1 million, that could be true. And yet at the same time, maybe I just want to eat a worm for fun, right? That's a logical possibility. It's not likely empirically, right? It's not probable, but it's a logical possibility. That doesn't violate my promise that I will also eat a worm if you give me $1 million or 100K, right? I could just eat worms for fun, but my promise would still be true that if you give me that money, I will again eat a worm, right? So that's World 3. I have not gone back on my promise to eat a worm for $1 million, right? World 4, that's the world we actually live in when it comes to the worm thing, right? You're not giving me 100K. Prove me wrong if you want to, right? I'm not eating a worm. Right? But my statement is true that if you gave me 100K, I would eat a worm, right? So this is the thing to remember about conditionals. And I explain this so much because people get confused about conditionals. They seem kind of weird, right? How can it be that a conditional is just going to be automatically true, right? For example, you can just make a true conditional by making the antecedent false. That is a bit weird, right? So I could just come up with a statement, a nonsensical kind of a statement, but it has to be true because of the way that we're defining conditionals, right? So I could say, if the moon is made out of cheese, then I have 2 hands, right? That's kind of a weird statement. Is that true? Well, by default, it's true because the moon isn't made out of green cheese, so that rule has not been violated, right? That statement has not been contradicted, so it gets to just be true by default. That is a bit weird, but it's more clear when you use an example like the worm thing, right? Hopefully that's clear to you. If it doesn't make intuitive sense, right, which I think it does for and or. Those people just know how to. I say it's sunny and warm. You know that they both have to be true, right? That's just, you just know that, right? This one is a little bit weirder. If it doesn't totally make intuitive sense, then just remember the rule. An antecedent is only false in World 2. Sorry, a conditional. A conditional is only false in world 2. Otherwise, they're true, right? A conditional is only false when the rule has been broken. Conditional is only false when the antecedent is true and the consequence is false. At the very least, just memorize the rule. It's much better if you see the logic of it, right? If you understand it on an intuitive level, that's always better. But if you can't, then at least just get it into your head what the rule is for conditionals, right? So that if I ask you, do a truth table for a conditional, you'll know, okay, I'm going to take my P and my Q, I'm going to fill it out according to the pattern, right? TTFF, TFTF. Then I'm going to take my conditional for a ride, right? Take it for a spin through logical space to each of the quadrants. And the rule is it's going to be true in all possible worlds except for world 2, where the antecedent P is true and the consequent Q is false. Right, so we have the truth tables. You should know the truth tables, but to help you remember the truth tables, you can also just know the rules in English, just like this, right? The rule for conditionals is a conditional is only false when the antecedent is true and the consequent is false, right? Try to remember that. Or if you can remember the worlds, right? A conditional is only false in world 2. And in all other cases, it's true, right? In any other situation, it's true. The rule for conjunctions and statements, a conjunction is only true when both conjuncts are true. So conditionals, it's easier to define it in terms of when it's false, right? Because there's just one scenario. So that means you only have to remember one thing, right? Conditionals are only false in this situation where A is true and B is false, right? Conjunctions, they're only true in one situation, when both things are true. And, or, a conjunction is only true in world 1, because world 1, true world, where they're both true. And for the disjunction, a disjunction is only false when both disjuncts are false, right? So again, because disjunctions are easily true, right, we just remember the one rule for when they're false, just like for a conditional. Right? So a disjunction is only false in that one world where both of the disjuncts are false. That's world 4. So, right, so try to remember each of these rules and then try to know what that looks like in a truth table if you were to set it up. So the negations, as I said, they're a little bit different, right? Negations just negate a statement. They don't join together two statements, right? It's not the sandwich effect here. Now, negations can negate complex statements. We'll get to that later. But the important thing here is that they don't join together two statements. You don't have P negative Q, right? That wouldn't make any sense. Right? P and Q, that makes sense. P or Q, that makes sense. If P, then Q, that makes sense. P not Q, no, that doesn't make any sense. Right? So we need to simplify things here. Right? We need to change the truth table because we're not dealing with two variables now. Right? We're dealing with just one variable because we're just negating a simple statement with our negation operator. And when you have one statement, right, there's just two possible worlds. Right? Maybe the statement is true. Possible world 2. Maybe the statement is false, right? It's 4 when you have two statements, right? And every time you add a statement, it doubles, by the way. So if you have one statement, there's two possible worlds. It could be true or false. If there's two statements, P and Q, there's 4 worlds. They could both be true, right? They could take turns in world 2 and 3, and then in world 4, they're both false. If we have 3 statements, P, Q, and R, then suddenly we have 8 different possible worlds. If we have 4 statements, then suddenly we have 16 possible worlds. Now, I can tell you now, we're not going to be doing that, right? We're not going to be doing, maybe as an example, I'll show you what 8 looks like, but once we have that many possibilities, once our arguments are that complex that they have more than two variables, then we have to change our technique a little bit. But it's good to start out like this, right? So that we know with one statement, it can be true or false. With two statements, right, there's four different combinations possible. Right? So then when we go to define our negation symbol, we'll do the same thing, right? We say, okay, let's say I say not P, right? Let's say I say it's not sunny. Then that means P stands for it's sunny, right? So if I look at the possibilities, if P means it's sunny, possible world 1 means it is sunny in that world. Possible world 2, it's not sunny, right? Then if I say it's not sunny, and I'm in possible world 1, then I said something false, right? In possible world 1, it is sunny, right? So if I'm in that world and I'm telling people it's not sunny, right? If I say it's not P, then what I said was something false. I hope that's clear. So the negation just flips the truth value, right? If P is true, then not P would be false. If P is false, then not P would be true. Right? Just flips it. That's all it does. Very, very simple, but it is one of these things where when you explain it, it almost sounds more complicated than the other ones. But it's not. It's very, very simple, right? Again, if we're in a world where it's sunny, and I say it's not sunny, then I said something false, right? That's world 1, right? Where if P stands for it's sunny, and we're in world 1 where that's true, so we're in a world where it is sunny, and then I come along, right? I'm going for a ride through logical space, and here I am visiting this first corner, and I tell people, I announce it's not sunny, right? Then my statement is false. Right? That statement is false in that world. On the other hand, right, if it is not sunny, right, that's possible world 2, where it's not sunny. I come along in that world and I say it's not sunny. Right? Then what I said was true. So we're defining it just like we did for the other ones. It's just slightly different because it's a single variable that we're dealing with, right? And so the rule for negations just is, it's just going to flip the truth value. Okay. So having that in the back of your mind, you're just about ready. There's a couple more things we could kind of do just to make sure that you're ready, right? So for example, with this knowledge, you should be able to, if I give you a compound or complex statement, and if I tell you what the truth value of the simple statements is, then you should be able to determine the truth value of the whole statement, right? So for example, let's say we're in world 1, right? Let's say, oh no, sorry, we're in world 4, right? Let's say P and Q are both false. Okay? I tell you that. Just assume P and Q are both false. What then is the truth value of P or Q, right? If that's your statement. Well, that statement is saying that either P or Q is true. Remember the rule for disjunctions? They're only false if both are false. Well, in this case, we're saying that they're both false, right? The rule for disjunction is a disjunction is only false if both of the disjuncts are false. And here we're saying P and Q are both false. So you should be able to infer, right, use your logical mind, that P or Q, that statement would be false. If I'm in a world where P and Q are not true, and I say, hey, everybody, either P or Q is true, maybe both, then I said something false, right? Because it's not true. Okay, let's still on the assumption that P and Q are false, right? I could also switch that around, right? I could also say, imagine that P and Q are both true, right? Or imagine that P is true and Q is false. I could set it up any way that I want, right? I'm selecting one of the possible worlds and then asking you what is the truth value in that world. So let's say they're both false. What is the truth value of if P then Q? Well, if you remember the rule, the rule for conditionals, then you would know that it would be true, right? Even if both the antecedent and the consequent are false, the whole conditional is still true. Because remember, the rule is a conditional is only false in world 2, where the antecedent P is true and the consequent Q is false. Right? But that's not the case here. P and Q are both false. And when P and Q are both false, that's world 4, the conditional is true. Right? Remember, that's the world we live in when it comes to our little worm deal. Right? If you give me 100K, then I will eat a worm. Okay? That statement is true, I promise you. But here we are, right? You didn't give me 100K, and I'm not eating a worm. P and Q are both false, but the conditional is true, because if you gave me that money, then I would eat that worm. It gets also a little bit more complex because, again, this is a shorter class. I'm not dealing that much with more difficult stuff. I'm giving you a very, very easy version of logic, so we don't have to worry too much about very, very complex things. But like, what if we had this, right? Not P or Q. And we haven't really looked at statements like that yet. Right, so let's assume again that P and Q are both false. And now we are in that world, in that fourth world, and I'm saying either not P or Q. That's basically saying either P is false or Q is true, right? When you say Q, it just means Q is true, right? When you say not P, you're saying P is false. So this time I'm saying either P is false or Q is true. Well, in that world, Q is false. And I had said not P, right? I had said that P is false. So then the statement will be true, right? So we could try here. I have my whiteboard here. I'm going to start using this more. One way to look at this is like this. Sorry. If we have our truth table, P and Q, and I go T, T, F, F, right? And here I go T, F, T, F. So I get all the 4 worlds, right? Hopefully that's clear. Then if my statement is not P or Q, well, then I could just fill it out the same way as normal, right? I could go, well, P is true, but I'm saying not P, right? So if P is true, then not P is false. So I could put a little false right here. And I could just put a T underneath Q. That would be world 1. Now, of course, we're just interested in the one where P and Q are both false, right? So let's not even look at these ones. If we're supposed to imagine that P and Q are both false, then yeah, I could put a little F underneath P to remind myself that that one's false, and I could put a little P underneath Q to remind myself that that one's false. But then I could put a true underneath this one. And this tells us the truth value of this whole disjunct. Because in this case, the disjunct isn't P, right? The disjunct now is this statement here, not P. So one disjunct is true, and the other disjunct is false. Well, what is the rule for a disjunction? As long as one side is true, then the whole thing gets to be true, right? We do have one side being true, right? So we can say, okay, the whole thing is true. So let me do this a different way, just to make this clear. Again, I showed you that we could set up the whole truth table if we wanted to, right? We could fill it all out if we needed to. We'll do that later for the arguments. But in this case, I said, let's imagine we're in the world where P and Q are both false, right? We're in that fourth world. So we're in world 4, right? Where P is false and Q is false. So I could go back to this one, right? The P or Q. If this is it, then I could say, okay, well, P is false and Q is false. Okay, well, what does my truth table for the disjunction look like? Well, in the truth table for disjunction, if both sides are false, then the whole thing is false. Right? Disjunctions are false when both sides are false, right? Like that. But this time I said, what if we have not P or Q? Right? Now we have a different disjunct on this side. You should remember that, right? That this forms a new, not compound, but complex statement. Right? This is a new statement now. So the statement on one side now says not P, and this statement still says Q. We're still in this world because I said, imagine we're in a world where P and Q are both false, right? Well, now when we fill it in, we can do the same thing. We can remind ourselves, oh yeah, P is false in this world, and Q is false in this world. But this left disjunct is not P, right? It's not P. I know that gets confusing. So I should put my true under here, and this tells me the truth value of the left disjunct, and this gives me the truth value of the right disjunct. Now I can ask, is this statement true or false? Right? Well, the rule for disjunctions is as long as one of the disjuncts is true, then the whole statement is true. And this time, because the false statement is being negated, we have a truth on one side. So now we've turned it into a true statement. Okay. Hopefully you get that. Right? If I had said, hey, let's assume P and Q are both true, both false, then we know, because of how the negation works, it just flips the truth value, then we know that not P must be true. And if not P is one of the disjuncts, then we have a true disjunct, right? And that's all you need for a true disjunction. Now here you see how it's starting to get more like logic, right? Because we're starting to work more with variables and signs and keeping track of the truths and falses, and it can get a little bit more overwhelming. And that's why I try to keep it simple in a class like this. Right? So let me do one of these with you, actually. Right? This is basically what we just did, but this is what I want you to do. Let me do one of the more difficult ones here. A and not Q. Right? So we have one conjunct, right? Here we have the conjunction operator. And I think you know what to do if it was like this, right? But we are now saying that one of the conjuncts is a negative statement. It's a negation, not Q. So now it's asserting A and not Q. Right? Another way of saying that is it's saying A is true, but Q is false. Right? That's what it's telling us. But now we have to look at what it says. Let's say statements A, B, and C are true, and let's say P, Q, and R are false. Okay, so A. It says A we should assume is true. Right? So we can put a little T underneath of it to remind ourselves that A is true in this scenario. And then P, Q, and R are false. Okay, so we put a little false underneath the Q. Now we need to ask ourselves, is this whole statement true or false? Well, we don't quite yet know, right? We've determined the truth value of this conjunct, right? That's T, true. But this conjunct we haven't figured out yet, because all we know is that Q is false. But Q is not the conjunct, right? The conjunct is not Q. So then we have to look at our truth table, our rule for negations, and we know that it just flips the truth value of whatever we're negating. So if Q is false, then not Q as a statement is going to be true. And then we can circle that. Well, however you want to keep track, right? That's up to you. I circle things or underline it. But now we know, right? Now we know we're dealing with a conjunct where both of the conjunction where both of the conjuncts are true. And what's our rule for conjunction? A conjunction is true only if both are true. But in this case, they are both true. And notice that would be different if it had just said this, A or Q, right? If this was it, and then we'd say, okay, let's say statements A, B, and C are true, P, Q, and R are false. Okay, A is true. Let's keep track of that. P, Q, and R are false. This is false. Okay. Then we could say, okay, this is the truth value of one of the conjuncts. This is the truth value of the other conjunct. Now the whole statement is not true, right? Because for conjunction to be true, both have to be true. Right? So now we'd have to say the whole thing is false. But it changed everything by adding a little negation in there, right? Because if we negate Q, then suddenly this conjunct becomes true, and then they are both true. Okay, so just use your logic and use your knowledge of these statements to deter of the operators, right? Use your knowledge of how to define the operators with truth tables to determine the truth value for each of these, on the assumption that A, B, and C are true, P, Q, and R are false, right? So I'll go ahead and try to do that. And I think that's all I have written. Right. I think maybe what I'll do here for the people that are totally crystal clear on everything that's going on so far, I'm going to jump into just showing you one truth table, maybe two, for arguments, right? Just to show you how it works. But I'll return to this and I'll put more on my actual slideshow. Right? And I hope you're all reading the book as well, right? And if you are getting everything from the book and you're not having a problem with anything, you don't even have to necessarily watch everything because I talk through things so much, right? That's not necessary for everybody. I have this kind of an obsession with making sure that everyone can get it if they want to, right? That I'm taking my time with every little thing, so that if you are following along, even if it's a little bit tedious sometimes, you will get it, right? That's why I over-explain things sometimes. But if you don't need that over-explanation, if you're making progress just going off the book, that's totally fine. So here, the whole idea is, can we prove if an argument is valid or invalid? So let's just start with one that we already know is valid, right? Just because it's very familiar, hopefully. Let's start with a modus ponens, right? Hopefully, if I say modus ponens, you should just know what argument format that is, right? You definitely should. We're going to do the sort of midtermy kind of a quiz in a couple days. You need to know at this point, right, what the 6 different argument formats are. So for a modus ponens, you should know that it goes if A, then B, A, therefore B, right? So if we translate it into logic speak, and this time we're not going to do the premise conclusion format where I go premise, conclusion. Right? That's helpful for when it's in English, but when we translate to logic and when we do logic, we want to write it across like this. So our first premise is if A, then B, right? So how do we write that in logic speak? Well, use an A. Sorry, I'm gonna a little bit more over here. A, and then the arrow, right? If A, then B. Then comma, that tells me the next premise is coming, okay? It's very important that you get the formatting of this right. If A, then B, comma, that tells me there's another premise, A, and then the therefore sign, right? Our conclusion indicator, the 3 dots. That means everything here is premises, right? There's 2 premises separated by a comma, and then our conclusion is B. So hopefully you can read this, right? 2 premises. If A, then B, A. Therefore, conclusion B. Okay? So anything after the three dots is a conclusion. So this would be your first step. If I say evaluate a deductive argument using a truth table, this would be your first step. Translate the argument into logical language using variables and the different operators. In this case, we have a conditional operator. Write it out like that. Then what we can do is, well, since for now we're just dealing with arguments that just have two variables, we have A and B, then we can create our worlds, right? We can do our little world thing. Go A and B, sort of separate it so you kind of understand, right? Here's the argument. Here's just the different truth values for A and B, right? And we'll do that the usual way. Underneath the first statement, I go T, T, F, F. Under the second one, I go T, F, T, F. Right? Two in a row, right? Here, alternating every time. And this is world 1, right? World 2, world 3, world 4, right? I didn't write those, but that should be apparent to you, right? That this is 1, 2, 3, 4. First world, they're always true. Fourth world, they're always false, right? 2 and 3, they sort of take turns. Okay. So now we could do a truth table for this whole thing, right? We can take this statement and take it for a spin through each of these worlds and see what it looks like. Right? Then that will reveal to us all the different possibilities for the truth value of the premises and the conclusion. Because remember, in a deductive argument, you're never going to get true premises and a false conclusion. Right? It's just not possible. So here we're going to look at all the possibilities. And there's only 4, right? Because we have 2 simple statements, there's only 4 possibilities. So even if we don't know if this statement is true, we don't know if this statement is true, it doesn't matter. We can look at all the logical possibilities. So let's look at world 1, where both of them are true. Okay, so let me put, the textbook doesn't quite do it like this, but this is the way that I think helps the most to keep track of it. I'll be showing you this technique. You could just go, okay, well, let's think about the truth table for if A then B. Is a conditional true when both the antecedent and the consequent are true? Well, yes, it is, right? So you could just go like this. You could also, I'm not quite sure if I want to do it the way that the book does it or the way that I usually do it. I guess because we're trying to stay close to the book, let's just do it like that. Okay, I talked myself out of doing it a certain way. We're in world 1, right? And we're trying to figure out, well, in world 1, what's the truth value of this statement right here, this premise, if A then B? Well, go back to your truth table for conditionals. Right? And remember, the rule for conditionals is they're only false in world 2, where the antecedent is true and the consequent is false. Right? So if you are giving me a worm and I'm eating if you're giving me $1 million and I'm eating the worm, right, then the statement is true. So in world 1, this conditional is true. In this world 1, A is true. And in this world, B is true. So possibility number 1 has the premise being true, this premise true, and the conclusion true. No problem, right? What we're looking for is the gremlin. Right? The gremlin pattern would go true, true, false. Right? So far, we have not discovered a problem yet. We have not discovered a gremlin, right? So now let's move on, right? Let's take our whole argument to this quadrant of logical space, where A is true and B is false. Okay, so we're in this world where A is true and B is false. What's the truth value of the conditional in that world? It's going to be false, right? That's the only world where conditionals are false. Okay, so I'll just circle it. Circling it here for me just means that that's the premise value or the conclusion value. Right? It's not the value of A or B. It's the value of if A then B, because the first premise is a conditional. Here I'm circling it because the premise just is a simple statement. Right? So again, look what we're doing, right? If A, then B. What's the truth value in world 2? Well, that's where the antecedent is true and the consequent is false. That's the only time that a conditional is false. So we can put a false there. Right? And in fact, you could just copy your truth table, right? We already know that the truth table for a conditional looks like TF, T, T, right? But let's just do line by line. But you could do it that way as well, right? Okay, so we're in world 2, where the first premise is false. That's a possibility. And A is true, right, in this world. Circle that. And B is false in this world. So we get a false conclusion, but one of the premises is also false. So one of the logical possibilities for any argument that looks like this is that A and B are both true. Well, if that's the case, we don't see any kind of problem. Maybe A is true and B is false, right? That's this possibility. In that case, this premise turns out to be false. This one's true, the conclusion's false. But that's fine, right? Because validity just means it's not possible for the premises to be true and the conclusion to be false. So all we're looking for is a pattern that goes TTF. If we don't see that, then there's no problem. So we have not seen a problem. So in world 3 now, where the antecedent is false and the consequent is true. Right? Well, in that world, the conditional is also true. Again, this is just going off those truth tables that we just went over, right? That's all this is. And this is basically just copying the truth table for a conditional. World 4, where the antecedent is false and the consequent is false, the whole statement is also true. So here we can see our truth table, right? And the rule for a conditional is it's only false when the antecedent is true and the consequent is false. Right? That's only in world 2. Now we're in world 3. Right? This one is true. What about A? Well, A is false in this world. Okay. What about B? B is true in this world. Do we see a gremlin yet? Do we see a TTF? No, we do not. Right? So far, this argument is looking good. Almost done here. Right? The final world where both are true. Right? It's fine. Then that one's true. A is false in that world. And B is false in that world. Okay, we did it. We took this argument format and we looked at all the possibilities that there are. For any two statements, A and B, there's only going to be 4 possibilities, and we checked them all out. We checked each possibility, and never was it possible to get TTF as long as we're following the rules of logic. This argument format is just resistant to that. It doesn't show us a gremlin, right? And as long as it doesn't show us a gremlin, we can say that it is valid, right? This argument is valid because we have shown that there's no possible way to get true premises and a false conclusion. And remember what the definition of validity is, right? In a valid argument, it is not possible for the premises to be true and the conclusion to be false. Or the truth of the premises guarantees the truth of the conclusion. And we can see that here, right? There's only one world where both of the premises are actually true, right? So it's true, right? The truth of the premises, where both of the premises are true, we are guaranteed to get it true. Because nowhere else did we get a T, and an F, right? If we got a T and an F, then the truth of the premises would not guarantee the truth of the conclusion. But here, when we see true premises, we only see a true conclusion. Right? Now, in some arguments, you might not even see that, but that doesn't matter as long as you don't see TTF, right? So let me make that clear. You don't need to see a TTT. It just kind of confirms it, right? But it's not necessary. You don't always see that. What you're ultimately only interested in is the pattern that goes T, T for the premises and then F for the conclusion, right? And so to show you that, I can just very easily change this argument, and then we'll be done, okay? Change this argument here. Since we're still just using 2 variables, A and B, I can leave all this the same, right? This always just looks that same way. Anytime we have two variables, it'll just look like this. So I can just leave this, but maybe we'll turn this into, I can keep the B, sorry. Turn this into affirming the consequent, right? Now, hopefully you remember that affirming the consequent is not valid, right? So you should be able to predict from the fact that you already know that this argument form is invalid, it's not valid, that this will allow for the possibility of true premises and a false conclusion. Okay? So here we should expect to find a gremlin, right? Again, a gremlin is that pattern that you're looking for, right? So that is just the rule, right? To do this, you're not looking for true premises and a true conclusion. That's irrelevant. The only thing you're looking for is true premises and a false conclusion. If you find that, the argument is invalid. If you don't find it, then the argument is valid, right? So it's only kind of exciting when it's invalid because you get to spot the gremlin, and that's somehow, sometimes, for some people, exciting. Right? So we'll just do the same thing. Right? We're in world one, where A and B are both true. So I can go A true, B true. Well, remember, we're not doing it that way. That's the way I'm used to doing it, but the book doesn't do it that way. We can just go, okay, well, if A is true and B is true, then what's the truth value of this whole thing? It's going to be true. Let me circle that just to keep track. In world one, B is true, and A is also true. Okay, no problem so far. We don't have a TTF, right? So far we're good. Now, how about world number two, where A is true and B is false? Well, remember, that's the world where conditionals are false, right? Conditionals are only false when A is true and B is false. So we make it false for there. And then B in that world is false. And A in that world is true. Okay. Still no gremlin pattern, right? No problem yet. Okay. What about world three? Well, world three, the conditional is true, right? Because remember, conditional is only false in world two. It'll always be true in world three. If we've set it up this way, then we know that, right? So it's true. And B in this world is also true. What about A? Well, in this world, A is false. Uh-oh. Boom. TTF. All the premises are true, but the conclusion is false. Gremlin. Right? Invalid. Right? Because here, the truth of the conclusion does not guarantee, the truth of the premises does not guarantee the truth of the conclusion. Right? Maybe the premises are true and the conclusion is true, but also the premises could be true and the conclusion is false. Right? And so if you come across an argument like this, even if you know that the premises are true, you can't trust that the conclusion logically follows. It doesn't. It's totally possible for both of the premises to be true and the conclusion is false. So that's why you reject this kind of argument. It's not reliable. Right? A valid argument format is like a machine that when you feed it truth, it only ever spits out truth. Right? It only ever gives you truth. That's what we saw with the previous one, where both of the premises are true, we see a true conclusion. And it's never the case that we get a false conclusion. Here, right, we can feed this argument format true premises, and it could spit out a false conclusion. Right? Valid argument forms don't do that, right? So valid argument forms are like truth machines that you feed it truths, and another truth comes out every single time. Right? That's why we use valid argument formats. They're truth machines, and we're after truth and accuracy. Right? In a valid argument form, if the premises are true, right, what you're feeding it, then you're guaranteed to have a true conclusion. It's not logically possible for the premises to be true and the conclusion to be false. But here, it is logically possible. We just showed it, right? And once you find a gremlin, you don't even need to do the rest of it because you've already proven that it's invalid. So the rest of it is not going to make any difference, right? So this is how every single one of these is done, right? When we're using the truth table method, where there's two variables, we're just laying out all the logical possibilities. That's all we're doing each time, and we're looking specifically for gremlins. We're looking only for this pattern. That's the only pattern we're interested in. We're not interested in this pattern at all, actually. Right? That goes back again to this weird counterintuitive idea that we should look for breaks in patterns rather than for patterns, right? It goes back to Socrates. It goes back to the scientific revolution when we figured out that it's more important to try to falsify something than it is to try to find evidence for it in a certain way, right? In this case, what we're looking for is to falsify it. And if we can, right, then we know the argument is invalid. If we can't, like for the previous one, right, we tried, but it just did not reveal a gremlin. So the previous argument format, the modus ponens, it just couldn't generate a gremlin, so that means it's valid. Here we have a gremlin, so it's invalid, right? Okay, so we'll do more of this next time, but I just want you to keep in mind, right? Maybe some of this stuff is hard to keep track of, but at the very least, in terms of playing the game of propositional logic, the ultimate goal is determine if the argument is valid or invalid. Right? How do you do that? Well, you map out the argument and take it through logical space and see if you can find a gremlin. Right? You're going to look in each of the four corners and see if you can spot a gremlin. Here we saw one in the third quadrant. Right? So we're in our logical spaceship. Right? We're going through the four corners of logical space, and we're looking for one thing only. We're looking for gremlins. Right? A gremlin is this pattern, TTF. If you don't find the gremlin, there's no problem. Everything is fine. Argument is valid. If we do find it, it's not fine. The argument is invalid. Okay. And with that, yeah, I think we'll stop here. But I'll explain this again, and maybe I'll do a little bit on the slideshow. But for a lot of the propositional logic, it's going to be a lot easier just to use the whiteboard because you can sort of see it in action. And it's actually very, very difficult and time-consuming to do this on the Prezi. So yeah. Okay. Well, I'll see you all soon.